Hello, today we're going to talk about quantified constraints. We're going to talk about when to use them and how to use them. This is a topic that's near and dear to my heart. In fact, there's a GET ticket on a particular application of quantified constraints where people started calling it Etsko's dream. So today we're going to talk about my dream. We can't hear you, Andres.
Oh, sorry.
Doesn't matter. No worries.
Welcome to the Haskell Unfolder YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and to discuss them.
Right. So let me start with an example from the original paper that introduced quantified constraints. There's a link in the video description, which is about monad transformers. This is possibly the most simple example, but possibly also the least practically useful, but it's a nice introduction. So most of us, I guess, are familiar with the monad transformer class, right? So we say that T is a monad transformer if we can take an action in the underlying monad M, and we
can't see the screen. Let's go.
Oh yeah. Sorry. We can lift it into the larger monad T of M, right? So we have an action in the underlying monad, and then we lift it into T of M. And we only need to do that if M is a monad, right? So any action in the underlying monad M, we can lift to T of M. Okay, most of us are familiar.
So a monad transformer is something like state T, right? Or
state T, reader T. Yeah, there's a whole bunch of these. Yeah.
Okay. Yeah. Okay. I guess it's reasonable to assume that if you start from a monad, say IO, then reader T of IO is a monad again. That is what you want to express, right?
Right. Well, that's what we want to express, right? But what you just said is that if we start with a monad like IO and we turn it into state T of IO, we still have a monad. That's not really what this class says at the moment. Right? This class just says that if M is a monad, then we can lift actions in the underlying monad into the larger monad, into the transformed monad, which actually is a problem, which is precisely what I want to talk about. So suppose that we have a way to stack monad transformers, right? So we have two monad transformers, T1 and T2, some underlying monad M, and some result A. And this is just a new type, right, where we just literally stack them together, right? T1 of T2 of M. And now what we would like to say is that if T2 and T1 are both monad transformers, then the stack thing is also a monad transformer. Right? That seems reasonable. I should be able to combine like state T of reader T of IO, for example, right? And if you think about it, this should be easy, right? All we need to do is give you a lift from M into the bigger thing. And well, this has two monad transformers on top of each other, so we should just lift twice. Right, so we can try that. So we just lift twice, and then we need to wrap it in this new type, right? But if we do this, we have a type error here. I don't know if you can read this at the bottom here, but it says that we do not know if T2 of M is a monad. Now, why does that matter? I can only lift if the underlying thing is a monad. I've lifted once here into T2 of M. I now want to lift again, but I do not know if T2 of M is a monad. Right, so I get a type error here. Now, the first thing you might try to do is maybe we can define that instance, right? So maybe we could try something like instance, I don't know, if M is a monad and this is a monad transformer, then the transformed thing is also a monad.
Yeah.
Something like this, right? But this is actually not possible. I mean, there's applicative and functor instances to taken care of here as well, but this is not definable without knowing anything about T. So that's a problem. And even if it would be definable, it's still problematic because this would then overlap with any other instance that looks like one type applied to another type. Right? So it's both impossible and undesirable. So this is not going to work. So we need a different solution. Now, Anders said earlier.
But on the other hand, the monad constraint is needed, right? I mean, we can also not just get rid of the precondition because, again, like in order to define a concrete monad trans instance, we will we will have to rely on M being a monad in general, right? So
Yeah, I mean, you could
so
weaken
that's not,
this, of course,
yeah,
and this will go through, but now we will get into trouble when we are trying to
Mm-hmm.
define monad trans instances where we want that like that monad M constraint.
yeah,
All right. So what we really want to know is what Anna said earlier, right? If we take IO and wrap it in state T, we want to know that's still a monad. And we don't know that at the moment. So we would like to say that T of M is still a monad. But how are we going to do that? We need to have some sort of constraint here, right? Like monad T of something here, right? But T of what? And we don't have an M here on the outside. What we really want to know is that this is a monad for any M. And that's precisely what QuantifiedConstraint allows us to do. So we can say for all M, monad T of M as a constraint on monad trans. Now this doesn't go through because we now need to know that this stack thing is still a monad. So that's easy. We can just derive functor applicative a monad. And now this thing bad checks, right? We lift it once into T2 of M. This constraint tells us that no matter what M was, we still have a monad, and then we can lift it again.
Mm-hmm. And this is a quantified constraint, right?
This is a quantified
literally a quantified
this is the
constraint.
quantifier.
Yeah. Mm-hmm.
For all, it's a quantifier, a universal quantifier. All right. Right, that's the first example that I wanted to talk about. Let's look at the next example now. And by the way,
there's a question
yeah.
which we should perhaps just answer. So should it be...
Yes, that is absolutely right. That will be better. Yes, definitely. Yes.
Okay,
Thank you for that correction. Yes, thank you. I appreciate it. Yes, indeed. That constraint is here, but of course we also need it here. Absolutely.
Mm-hmm.
All right. Okay. Excuse my voice. I'm a little bit sick. The next example I want to talk about is a bit more practical, perhaps, and it's an example from a library called quickcheck-dynamic, which is a model-based testing library initially developed by the folks at QVic. And in this library, we have a class called state model, which is going to model a state, is going to describe a model that we're using for testing. So the way that this works is that we have some system that we want to test, maybe a web server, maybe a database, whatever, right? Some stateful system. And we're going to generate actions that allow us to interact with the system, create a table, ask for a user, whatever is necessary to interact with the system. And then we're going to execute it against the system, and we're also going to execute it against the model. And the model is going to tell us what the correct answer is at any point. And so that's the idea behind such a library. And so in order to do that, we need some way of describing what the actions are, right? So state here is the type of our model. And we need an associated data type that's going to describe what kind of actions are we going to run against our system, right? And so that's going to be an associated data type here. And this data type itself is a GDT, right? It has a type index. And that type index is going to tell us what the result of this action is. So that's perhaps a bit abstract. So let me give an example. Suppose that we are testing some sort of REST server, right? Like a web server. Then we might say that this is an instance of our state model. This is our model here, right? So we're like whatever this is. Doesn't matter for the sake of this demonstration here. So we might say, okay, the actions that we have for our REST server is we might have an add user. Maybe this is a REST put call, right? We have a username, and then we get back maybe the user ID. And maybe we have a get request that takes a user ID and then gets us back username.
Mm-hmm.
Sorry. All right. And perhaps we have one final one, which is that doesn't have any arguments at all and just gets us all the usernames. Right, so the point here is that we have this action thing, and the result type here tells us what the result of this action is.
Mm-hmm.
All right. Now, if you think about it, in such a library, what we want to do is we're going to generate random actions. We're going to execute them. and then we're going to check them against the model. And if we find a failure, right, meaning the model gives us one answer, but the system gives us a different answer, we want to show which actions we executed, right? That's going to be important. So we want a constraint on this thing here that says that this action thing must be showable.
Yeah.
Okay, so we can say show action state, but what is going to be the type argument? Right? It's unclear. Excuse me. For this,
I guess we could enumerate them.
yeah, if we knew what the thing was, we could enumerate them, right? Int and string here, but we don't know anything about that here, right? This
Right,
is
because it's an instance, yeah, and we need it in the class, yeah.
Yeah, we don't know that here. So really what we want is that this is showable no matter what the result type is. So that's another quantified constraint, and we say that for any A, this action must be showable. Now we're getting a type error here because this action is not showable, but that's easily solved. We can just derive the show instance.
Okay. So I'm wondering what would happen if we had a constructor that mentions the A?
Yeah, that's a good question. So we don't have a type error now anymore because we insist that it's showable for any A, and indeed our show instance does indeed work for any A, right? If we had something like this, well, it's showable for int, it's showable for string, and it's showable for a list of strings. That covers all our cases, right? But it's still not good enough because we need to show it for all A. So what Anders said, so we have some other thing here that says, well, if we have an A, then might we have some, I don't know, maybe an identity action that just gets you an A and just gives you back that same A. Right now we have a problem because now this thing is not showable anymore for any A. Right? This particular case is a problem because this A is not showable.
Right.
But we could fix this by just having a local constraint that says that A must be showable. So that's a way to do this for polymorphic arguments, but typically we don't need this.
Okay. But we wouldn't want to put the show A into the quantified constraint because that would be too limiting, right? Or
yeah, we might have something like
I mean, we could fix it, I guess. Like rather than putting the show A constraint, we could put the show A constraint up in the class, but that would
we could do this.
But that would be undesirable.
Correction that I had earlier about the monad, right?
Yeah.
But now, if we have something like, I don't know, maybe something that has an action, maybe it has a function that an action that actually gives us a function or something.
Right. Now
in this case, the function is not showable, but the action is still showable.
Right.
So we don't really.
So now, if we put the show A up there, we would not be able to do it. Yeah, no, that makes sense.
Yeah, we would. Yeah. All right. So once we have this, now if I just to show you that it works, if I have some state model that I don't know anything about, an action in that state model, I can just show it simply by calling show. Yeah, I want to show you two more examples. And the first one actually comes back to the question Anders just asked about, do we want to show a constraint, yes or no? So suppose that we have a data type of expressions, right? This is a GDT again. It's one of the classical examples of a GDT, right? Type expressions. And so maybe we have a value constructor that gives us any A in expression A, right? That's what we kind of had here earlier. And then maybe we have, I don't know, a way to add expressions. Maybe we have a way to check if two expressions are equal. I guess it's a bool back as arguments, right, as a result. And maybe we have a conditional. Right, and the conditional is polymorphic. And now, for example, you could imagine that we could define something like evaluator that takes an expression of an A and gives you back the A, right? I'll leave this as an exercise, easy exercise. By the way, I should say that all the examples that I'm showing you today are in the repository that goes with this series, and they are worked out in detail. So yeah, if you wanted to give it just a play with it, then that's there. Link in the
Yeah, there is a link in the description.
Yeah. Okay, so now suppose that we are writing a parser for this expression language. Right, so we might have parse expression, and it's parser of something. Right, but what is it going to be the something here? Again, in the repository, I actually write this parser. I'm not going to do that here. But I mean, one option is to have, if we know ahead of time what kind of expression we expect, like an int or a bool or whatever, then we can write a parser for that type. Right, that's possible. But if we don't know that, like maybe if the user writes an if, then maybe maybe the user writes an add, then maybe it's an int. If the user writes an equal sign at the very top level, then it's a bool, right? Maybe we don't want to pick ahead of time what kind of expression we're expecting. So what we want to say is that this is some expression for some type that we do not know. Some type that we're going to discover when we are parsing. So we could do that by introducing an existential type. And this is usually called sum. I'm going to call it sum showable for reasons that will become clear very shortly. So what we're going to do is we're going to have an f, and this f is going to have kind type to type, right? Something like expression. Or maybe even like something like maybe or list or whatever, right? Anything that takes a type as argument and gives you back a type. So we're going to have an f of a applied to some a, and that a is going to be invisible on the outside, right? So sum showable on the outside, the result of this constructor, the a does not appear. So we have an a here that we're not saying anything about on the outside, which is exactly what we want here, right? So we have some showable expression. Some. And I called it some showable because I'm going to do one more thing. I want to know that, yes, I don't know what this a is, but I do want to know that it's showable at least. So I'm going to have a show a constraint here. Right. So now let's think about what it would take to show something of type some showable expression. Right. So show some expression. I want to take something of this type here, just turn it into a string, and I just want to call show on it, right? So that means I need a show instance for this type here. Okay, well, let's try to do that. We can derive, right? So some constraints show some showable f, right? Now what we want to say here is that f of a must be showable. Right, because that's the thing that's inside here. But we don't have an a here. Right, so again, same problem, same solution. Right, so we say it doesn't matter what that a is. Any a that's showable, f of a must be showable. Right, now this works. I need an instance of this shape expression. I can do. Right, if you compare this line with this constraint, it matches exactly, right? For any a that's showable, expression of a is showable. And now this like this. And so just to bring home the point, like previously, we had something like for all a, show action of state of a. And then we said we don't really want a show a constraint here, because some actions might be showable even if a is not. Right? And if we then have a show a constraint on it, we would not be able to show the action because the a might not be showable, even though the action itself is perfectly showable. Right? So we don't really want a show a constraint here, right? We don't really want that here. On the other hand, for expressions here, we had a constraint of this shape. It seems weaker in this end, right? Expression a only has to be showable if a is showable. So for the implementer, this is weaker, right? We only have to show that it's showable for showable a's. But for the user, it's stronger, right? You can only show an expression if A is showable, right? So these two things really are incomparable. Sometimes you want one and sometimes you want the other.
And I guess, it's not even clear here, right? I mean, even for the expression data type, we might have a situation where we would like have a result type which would normally not be showable, but it's somehow not mentioned. Like no occurrence of this thing is mentioned, so it's not clear that there always is an optimal choice, right? But
yes, yeah. I mean, if we had, I don't know, ID here or something,
yeah.
right? And then we are back into trouble, right? Because now these things are not showable, right?
So we have another question by Sebastian, which like Tom Smading has already partially answered in the chat, but I'll nevertheless highlight it here as well in case you want to say something about this. Would the existential type still be useful without the show constraint, or is some constraint needed?
Yeah, it's a good question. So it depends very much on the application, right? I mean, definitely a type that's just called sum, where you have no constraints at all. Actually, it's frequently useful. But it very much depends on the application, right? Sometimes you want some constraints, sometimes you don't. So there's even a possibility of introducing, like making the constraint itself a parameter, right? That's quite a nice solution, I think. So now it's the user just picks which constraints they need.
So I guess there's a follow-up. I guess the question is how existentials are useful. So perhaps I can actually try to like answer this briefly myself. So here, like even if you wouldn't have the constraint, I would argue that it is still a little bit useful, because what you're capturing is that you're getting a well-typed expression as the parser, as the result of the parser. Right, so basically that is an additional property that the GADT here is expressing, and so that makes it less flexible. And even though you don't know the exact result type you're getting, just like purely by knowing that there is some valid result type, you know that okay, you have parsed whatever input successfully into a value of this data type. So your input must have been, at least if your value is a representation of the input, your input value must have been well typed. So in this case, there is some extra information attached to it. But you're right that, like, I mean, in general, existentials are usually only useful if you know some additional properties, and it's quite common that you want to have some additional constraints, and you can overuse them. I mean, you can certainly overuse them, and if like the better option may just be to express the constraints directly. But I guess that leads a little bit away from the topic of this episode. Perhaps we can do another episode on existentials at some point.
Yeah, just to close that topic, actually, if you look at the implementation, the full implementation for this episode, you will see that I wrote a parser for this, which actually is 2 phases, right? It's a parser for an untyped language, and there's a type checker that goes into the typed language. And since it gives me something of type X per A, I know my type checker must be correct, or at least, well, that's not entirely true. Of course, I could always say parse error or something, but I know that if it returns an expression, it must be type correct, because GHC guarantees that it is, right? I'm giving you a value of this type here, which GHC tells me is type correct. So yeah, that's actually in the repo. So if you want to take a look at that, that's there. All right. For the last example, the last couple of minutes, maybe we can hide that question, if you don't mind. Suppose that we are designing an application and we have an encryption layer. And we might want to swap that encryption layer for different implementations, right? Maybe we want, I don't know, AES encryption, maybe we want some other encryption, and maybe we want mock encryption, right? And that might be quite important, for example, for the performance of our test suite, right? If our test suite does a lot of encryption operations, that might get quite expensive, and that might make the test suite quite slow. And so we might want to swap encryption for a mock encryption that actually doesn't do any encryption, but has the same sort of API, but runs much faster. right? So we're going to do a class that does precisely that, that describes that concept. So E here is going to be a type level tag. It's not going to be anything at all, right? It's not some, we're never going to have values of this type. It's just going to be like a tag, right? It's this encryption or this other encryption. Yeah. All right. So we might have two type families in this class. One that says, okay, whatever this encryption is, we must have a type for keys in this encryption system. And the other thing we might have is that, well, if we encode something, then we have something of type enc, right? So enc is going to be the type of encoded values. So for example, encrypt takes a proxy for E, just to help the type inference along, the key, a value, and then returns the encrypted value. And you can imagine that decrypt goes the other way. And we might have, I don't know, maybe some serialization constraint on A here, right? I mean, or it's, for example, a serialization form designed specifically for encryption. So yeah, something like this. So just to give you an example, what that might look like, it's AES, for example, then the key might just be a byte string, and the encrypted value might just be a byte string as well. And then encrypts, I'm just going to leave undefined for now. Actually, there's a full implementation in REPL again. And maybe for mock, well, for mock, we're actually not going to do any encryption. So we'll just do something like this. Maybe the types, the keys, like you point out, just numbers, key 1, key 2, key 3, whatever. And then for the encrypted value, we're just going to pair the value with the key, right? So now encrypt is literally just this constructor here, right? And then in decrypt, you would check whether the key that we paired with it is equals the key that we are given, right? So a decrypt operation is one integer comparison and then nothing else, right? So if we have a test suite that is now using this, it will be much, much faster. Mm-hmm. Okay. But if we have a test suite, we probably want to compare values, right? Maybe we want to compare keys, maybe we want to compare encrypted values, things like this. We need E constraints. E constraint on the key is easy, right? That's not a problem at all. But what about this thing here? We want that the encrypted values are also comparable. And you might say, well, we've just seen you do this 10 times, so just do the same thing.
Yeah, so just add a quantifier.
Right, so you might want to think this is the obvious thing to do, right? And it is the obvious thing to do, and I feel like this should be the obvious thing to do, but unfortunately, GHG does not accept this.
So yeah, so let's see, we get illegal type synonym family application, enc and instance. So that is, so basically GHC just rules out type synonym families, basically type family applications in quantified constraints, or at least under certain circumstances.
Right? You cannot use any type families on the right-hand side of a quantifier. Yeah. I don't really understand the whys. There's a big ticket on this. This is the ticket I referred to in the introduction. But link in the description if you want to see it. All I want to show you here is that there's actually a workaround, and it's an easy workaround. The workaround is to define a class alias or a class new type. So what we're going to do is we're going to make a new class that captures precisely this concept, right? The encrypted value must be comparable. Mm-hmm. Right, so let's call it egenc. And we're going to say that egenc is satisfiable precisely when this is comparable.
Mm-hmm. Okay. And ETSCO is calling this a class synonym because basically it's a class and instance pair, which is just establishing an equivalence between the class we're just defining, egenc, and the sort of the precondition or the superclass, or however you want to call it, the expansion of ec of enc ea.
Right, exactly. Mm-hmm. And so now all we need to do here is, rather than using this type family directly, we can just use this class alias. Mm-hmm. And now we're done. And now we still have a type error because I didn't declare this to be showable. Let me be fixed. What did I do wrong?
Eek. Not show.
Yes.
Yeah.
Thank you.
Yeah.
So yeah, this
Okay.
workaround is not my invention. It was Iceland Jack and Ryan Scott who came up with this. So but it's a workaround that works, as far as I know, in all situations. There have been earlier workarounds proposed that do not work in all situations, but I have not yet come across a situation where this workaround does not work. So yeah.
Which seems to suggest that it should also be a surpassable restriction in the first place, right? But
I'm with you 100% there, but maybe the GHD experts can chime in on that. That brings us to 30 minutes on the dot. So are there any further questions?
I don't see one right now, so unless there is another one that appears, and I guess we can conclude. So
All right. Oh dear. Yes. Okay.
Okay. So thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to ask additional questions or leave comments, like in the comments, not in the chat then. And the next episode is going to be on injectivity on Monday the 15th of May. So I hope to see you back then.